So now let's talk about fractions. We know we have these three models and we're starting to get comfortable using the three different models. So, just in case we want some extra examples, we're going to do them now. So let's start with the set model. And I'm just going to draw it because you can use anything to represent your set. And so you can use the counters, you can use the square tiles in the pattern blocks. You can even use any of the other shapes in the pattern blocks. But when we see them as separate, discrete pieces, that's when we have the set model. And so if we want a set model with a defined whole, then we literally have a set that comes in a pack. So a pack of gum, a pack of markers, a pack of colored pencils, a pack of eggs or a dozen eggs, right? A carton of eggs, whatever you have a pack of, that you can create a fraction, right? Because you have a defined whole, you have a defined set, right? A set of the set. But if you don't, then you can just make one. And this is what I want to show here. So let's take a fraction like ninths. So let's try to show ninths. And so what we can think about is, well, if I have a set, I literally then just want 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now ninths, right? So this one thing is 1/9. And now you can just color. How many ninths do you want? Color them in. And that's literally how you start with this set model. That's why it's considered the most concrete, because we can just define our set and then start counting how many, right? The denominators, how many we have, the numerators, how many we want. So how many do we want? Say we want 4/9. 1, 2, 3, 4. Right? And now we see we have 4/9. And it don't overthink it. That's all it is. That's all the set model does. And that's the point of the set model. It's supposed to be the most concrete. But in that sense, it then is also it's not going to be the most flexible. So we're going to, and so if it's hard to see the next couple of things, that's why. Right? We can start really simple, like, okay, we're just going to call the thing, whatever the denominator is, have that many of that to make up our set. And that's also really important to note, right? This whole set is 1. That's our 9/9. That is our whole. And so we have to define the whole whenever we're using a set that doesn't, or any model that does not have a predefined whole, right? When it has the predefined whole, that means the whole is already defined for you. In this case, we defined this whole. But now let's talk about equivalence, right? This was what we've been working on this week, and this is what a lot of people are still working to understand is, well, how do I show equivalence? Say we want 4/9 is the same as 8/18. Well, if we look at the set that we just defined, well, we don't have an 18. We don't have 18 of anything. So we need to define the whole to be able to show both ninths and 18ths. We need to be able to say what any we need to be able to show both of these denominators so that way the wholes are exactly the same. And that's really, really, really important. So what we're going to do, and maybe I will kind of do it just below here so we can see them side by side, is now the same way we defined our ninth is going to be the same way we define our new set. And we want it of 18. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So now, if we define this as our whole, this set is 1, or we made it of 18/18, right? Then this little guy, the same size counter, and I just use a different color just for the sake, but it could be the same color, right? Is now called 1/18. When we have a set we partition it, and I'm just going to erase this around the edge, right? We partition it, and therefore we can find out what each of these pieces is called. So again, we want to see, well, actually, before I go there, so now if we look above, right, each one of these, each column, we have 9 of them. So each column is called 1/9. And that's exactly the same that's happening here. Each column here is 1/9. And I have 9 of them. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have cut my set. I have partitioned my whole into 9 equal pieces, right? So each of these is called, each column now is called 1/9. I have 9 of them, 9 equal partitions. And now, so I wanted to show 4 of them. So here's my 4. 1/9, right, is one column, 2/9, 3/9, and 4/9. So right here are my 4/9. And now I can see that is the same as 1, 2, 3, 4, 5, 6, 7, 8, 8/18. So we can see that in one set, or if that's not accessible, we can create another set, right? So now again, these are the same size whole. And what we can do is, if we wanted to look at 9ths in this first set, I'll erase this guy, right? We want to see this first set as 9ths. So 1/9, 2/9, 3/9, 4/9, 5/9, 6/9, 7/9, 8/9, 9/9, right? I want the whole column to be my 4/9. I have 4 columns. And now I'm thinking, okay, well, how is that shown as 18ths, right? One of these is, one of these little counters here is worth an 18th. So I'm going to see, how many 18ths do I have? 1, 2, 3, 4, 5, 6, 7, 8. So here I can see that this is now 8/18 because I'm counting each individual piece, and we can see that they are exactly the same. Exactly the same amount of the set is colored, is shaded, and that's how we can show this equivalence. We see the set is defined, each whole is the same, right? 18 out of an 18 there, right? The sets, the wholes are defined exactly the same, and therefore that's how we can show the equivalence. It's really how we're looking at the set to see those different denominators. So here we're looking at the set as here we're looking at the set, right? Here we're looking at every individual one, and over here we were looking at the columns to see the 9ths. We can also see halves, right? I can split this in half, right? The set, we see those 2 halves, if that's helpful to also show another example of where we can, how we can partition these set. You can also, you might even be able to see other things. Can you see thirds in this set? Can you see sixths in this set? So now let's see those same ideas in the other models. So we saw the set model. So again, immediately when we're in fraction circles, this is now the area model, but you see, boom, it automatically gives me a whole. So this has a predefined whole. I can type in 9, and now I see 9ths. If I now wanted to show equivalence, I wanted to see 18, I can type in 18, boom. So my 2 wholes are exactly the same size, and I want to look at the space that it takes up. So I can color it in, I can turn on, what were we saying? I think right? 4/9, and maybe I want that a different color, one, right? 4/9 is the same as, oopsie, wrong one. 8/18, and how do I see that? I see that because they have the exact same area, right? That's shaded. And that's how I see the equivalence in the area model. But now this is the predefined whole. And so I know you know how to use these. What I want you to do is practice with the pattern blocks. So just like with the set model, if I wanted to just show ninths, start with the smallest denominator and now name this. So we can start with the smallest fractional piece, and we can call that a ninth. However, we don't have to start with the smallest fractional piece. We could have called this guy 1/9. We could have called the hexagon 1/9, the trapezoid, right? If we do that, it changes what the whole looks like. So you have to define your piece and you iterate that piece. So go back and practice those partitioning and iterating practice from last week. You define your piece and now you can iterate that to find your whole. So we can do both of these examples. If the green triangle is 1/9, then I need 9 of them to make a whole. And so you can think like, okay, I can literally pull over 9 of these and arrange them in any way you want. That's really time consuming. So I'm going to think about, how do I do this in a more efficient way? Well, I know this guy right here is 6 green triangles, right? That's the relationship. And now if I want 9 green triangles, well, I know this guy right here is 3 green triangles, and 6 plus 3 is 9. So boom, if this is 1/9, then this awesome looking shape right here, sorry, that's a terrible outline, right? And I can, maybe you would like, I can even change the colors, right? Now this thing is my whole. This is 1 or my 9/9. When, right? When this guy is 1/9, it determines now my whole. Now, similar thinking, if this guy is 1/9, I need 9 of them to make my whole. And I'm like, okay, you can, again, pull over 9, count them out, rearrange them however you want. Likewise, right, I could have put this guy here. It doesn't matter. We're looking at this space that this shape takes up, right? That these shapes take up. How you put them together does not matter, as long as they are together and we're attending to the area. That's what makes it the area model. Or you can think about, okay, so if this guy is 1/9, I know 3 rhombi, parallelograms, fit into a hexagon. So here would be 3, here would be 6, here would be 9, right? And you can show this is a 9th by filling in all 9 of them. And then if you would like, we can highlight these. This down here duplicates it. And now you can see, duplicate it again, right? How this whole now makes this guy the 9th. And now I'm going to delete these. And so this, when the blue, when the rhombus, when the parallel or parallelogram, whichever you like to call it, when the blue one is 1/9, this now is my 9/9 or my whole, my 1. And then you can now think about, okay, well, if this is 1/9, what does that make this guy? What does that make this guy? And or look at the relationship. How many of the red ones fit into, oopsie, sorry, I'll pull that one back up, fit into this shape? 1, 2, 3, 4, 5, 6, right? So this guy is called 1/6. And then this guy, how many, you can count how many fit in, or you can count, 6, 12, 18, or you can think of how many of these green ones make up the blue one. Oh, half. Half of 1/9 is 1/18. And now you just did fraction multiplication, or if you thought of not 1/9 divided by 2, you just divided a fraction by a whole number and got 1/18. So this is where understanding the models is, and I know we're taking time and this may seem tedious or laborious, but it's so important because it's going to make understanding the operations then that much easier in a way, that much more intuitive, that much more helpful. And so we're going to do this same exact idea now. So this is the area model. This is the area model. And I know that you're like, it's so much easier if I just make the one circle and then type in the denominator. Yes, that's true. But then you're losing out on the reasoning, right? The reasoning between the relationship of the numerator and the denominator and the actual model, the space it takes up. Additionally, there's so many fractions that are just more than a circle. And fractions are more than just a circle. So again, using just one model can be limiting. We don't want to limit students' understanding. And so this is why we use more than one model. We want to use all of the models. We want to use ones with predefined holes and ones with not predefined holes. That's how we develop this conceptual, this deep understanding of the concepts. And so same idea, if we go to the length model, I can have this little rectangle, right? I'm no longer looking at the second dimension. I'm only looking across the pieces, and I want 9 of them, or I want 18 of them, right? Again, exactly the same reasoning we just used, right? It's a predefined hole. It's set 0 to 9, right? 0/9 to 9/9, 0/18 to 8/18 to 18/18. And they're literally the exact same length. That is so important. They have to be the same size in order to show that they are equivalent, in order to compare the fractions, right? And then we can color. We're looking at the length across. Look at that. They are the exact same length. Awesome. But we can do this same exact reasoning, right? Here we're showing 4/9 is the same as 8/18. And now practice. How do you explain why that's true? Think about, I know, sorry, we're going to get to the the length model without a predefined hole next, but I want to take a quick little slight tangent, right? Think about, how do we explain this procedure? When we multiply the numerator, multiply the denominator, right? We multiply them by the same number times 2 times 2, and that's how we produce these equivalent fractions, right? That's how we do it. That's the procedure. So how do we explain, how do the representations help us to show why that works the way it does? That's what I want you to practice. Why does that work the way it does? All right, so last example, is now the length model, but again, there's no predefined hole, right? I don't have anything here. I need to define what I want. So just like what we did with the set model, let's start with the small, and the set model didn't have a predefined hole. This area model in each instance doesn't have a predefined hole. So start with your, this is called a unit fraction, right? Start with the smallest unit. In this case, all unit fractions are not, doesn't mean the smallest unit. A unit fraction just means the numerator is 1. So you can start with the smallest unit. What do we want to call this guy? Do we want to call this guy 1/9? If we do, then that means our whole, right, would be 9 of them. And I'm leaving the numbers on just so you can see a reference, but I'm going to show you why leaving the numbers on is also going to be maybe just confusing, limiting. I might be overusing that phrase, right? So then this is our 9/9. This is our whole. So just like you did the set, right? You started with 1, you made 9 of them, and that became your set of 9, which was 9/9, and then you could show 9ths. You do the same thing with the Cuisenaire rods, the length model. But if we look here, if this is a 9th, I don't have anything smaller. How do I get an 18th, right? How do I show these equivalents? And so now I have to define my whole differently. if this now is my smallest, maybe I want to call that one now my 18th, right? This is now 1/18. And now my whole is going to be 18 of them. You guessed it, right? Here's 10, here's 8, boom. Now this is 18/18 or 1, right? This is 1 whole. 18, right? I can line up 18 of these all the way down here. And now I'm going to turn off the numbers, and so we can start reasoning about these lengths. So now we want to think about, how do I show equivalence? What are some of these other pieces? So what would this one be called? What would this one be called? Oh, and why did I skip this one? Why did I skip this one? Why am I going to jump right to this one? And then skip, jump right to this one. Oh, I'm running out of space. But here, we'll start here. What would this blue, here, this blue one was called 1. It was our whole, right? That's how we defined this fraction here. But if I notice, right, the flexibility with these pieces that don't have a predefined whole is that they can be anything. So if this whole length of an orange plus a brown is 1, what does this one become? If 2 of them make up the whole. If I can partition one thing into 2 equal pieces, what is each equal piece called? You got it. 1/2. Likewise, if I can, how many of these dark green ones will make up this whole? And this is why not having the numbers on might be able to help you, right? Because now you're focusing on the relationship instead of the numerical, instead of the length in numbers. Ooh, if there's 3 equal pieces, what's this one now called? You got it. Ooh, sorry, wrong button. I'm gonna show that in 1 second. 1/3. And here we can start, once we define a whole, we can start comparing. Oh, if this is 1/2 and this is 1/3, look, 1/2s are bigger than thirds, right? We can start making sense of the fraction as a number. What I want you to see also, so I'm going to turn the numbers on, right? And here's 18, right? The orange plus the brown is a length 18. So what do you think each length of the dark green ones are? What number times 3, right? 3 times will give me 18, or a number plus a number plus a number equals 18. You got it, 6, right? So what I mean by we don't always want the numbers on is because this is length 6, but your brain, by seeing a 6, might want to call it a 6th. It's not a 6th. You see 3 of them make up the whole. It is a 1/3. So that's why I want you to practice without the numbers on. You can use the numbers to make sure you have the equal lengths, or just line them up. And so likewise, what do you think this number is called? Or this, if you didn't notice, if you didn't see it, how many light greens make up the whole? 1, 2, 3, 4, 5, 6. How many light greens make up the whole? 6 of them, but what's their length? You can count it even, this is the beauty also of the grid paper. Count it, 1, 2, 3, right? The light green is length 3, but 6 of them make up the whole. So the light green is called, fill it in, you got it? Yes, right? 1/6. So now what is this guy called? How many of these, or maybe you don't even want to completely count it out. Line them all up. These are getting tiny. Well, I can tell you, right? Or you can see, right? This is length 2. So we have 1 fits in, 2 fits in, 3 fits in. How many are going to completely fill this whole thing? I know it's not lined up, right? 9 of them. So what is one of the red ones called? Sorry. Yep, 1/9. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And again, turn on the numbers. And maybe I should have done that when they were all lined up, right? 2 plus 2 plus 2, 2 9 times, right? 2 times 9, 2 9 times is the same as, is equivalent to, is equal to 18, right? So this is not, right? You, again, you want to see 2, but this is not a 2. This is called 1, right? 1/9, because 9 of them make up the whole. So just be very, very careful if you keep the numbers on, to be sure that they don't trick you, because my brain always wants to call it the length, the denominator, but it's actually the opposite. If you notice, right? Length 2, 9 of them make it up, but length 9, right? 2 of them, right? The length 9 is the half. The length 2 is a 9th. And that's length 3 is a 6th. Length 6 is a 3rd, right? That's not just a coincidence. That's this multiplicative relationship that I've been alluding to, or trying to bring your attention to.